Welcome back, guys. This particular video will look at the introduction to linear kinematic analysis of a 50-meter sprint. So the purpose of this particular practical is to have a specific setup that allows us to derive some really important information when it comes down to sprinting and sprinting times. So for example, the main objective of this particular prac is to find out what the maximum velocity is that a person was sprinting at, what their acceleration was, at what point in time did they start to decelerate, and what was the distance that they achieved where deceleration was ultimately zero. In other words, what point in time on the track did they start to decelerate. So we know that elite sprinters can maintain or only reach peak velocity at around about 60 meters and can maintain it for about 30 meters before ultimately starting to decelerate. So how does your data compare to that of elite distance runners? And that's what this prac will ultimately tend to unpack. So the instructions are all provided, and then at the end we have some of the analytical questions that you will need to answer in order to complete the prac. So what I will do is divide or just produce a couple of videos that just go through some of the theory, and then we'll look at how do we start applying that using some real life data in our analysis. Okay, so the setup looks something like what we have down here. So you can see, for example, we have a sprinter on a track. We have specific point markers allocated where we've placed specific timing gates at strategic points, right? So we have a timing gate that would initiate our timer. We have a timing gate at the 5-meter mark, 10-meter mark, 40-meter mark, and 50-meter mark. In an ideal world, you would have quite a few of these timing gates probably spaced out every 5 meters at least in order to get some really accurate data. This is going to give you a relatively good approximation, but it's not ideal, but it'll do for what we want to achieve for now, because it's the process of analyzing that we ultimately want to do. The sprinter would start behind the first timing gate with a standing start, and at the count of 3, 2, 1, go, they would sprint the entire distance as fast as possible, aiming for some point in time beyond the 50-meter mark, because we don't want them to slow down any time before then. Alright, and then the timing gates will give us what the specific time increment was at that specific distance. Ultimately what we would do is then we create a table and then plot our data, where we plot the position at any specific point in time in order to reconstruct this graph. What you should find is that the graph that you ultimately plot should almost follow this S type of a curve. The reason being is you'd notice that it takes quite a while for the person to build up speed. So the distance that they cover in the first few seconds is very, very little relative to the time that's elapsed. But as they kind of hit the middle of their sprint, they hit somewhere in here peak velocity. In other words, they are covering the greatest amount of distance relative to a period of time, and then ultimately as they start fatiguing, the amount of distance that they cover relative to a period of time is again starting to decrease. So it follows this S-type curve. Now what our goal is to ultimately use this position versus time data and the graph in order to find out what their velocity is at any point in time. And I'm not just talking about average velocity, I'm talking about instantaneous velocity. So what is their velocity at any instant in time? And similarly, what is the acceleration at any instant in time? Remember, our goal is to find out at what point in time along their sprint did they start to decelerate or have zero acceleration. So what you can imagine is, as this person sprinting, is that they have a slow start, their speed tends to build up, and then towards the end they start to slow down again, which means that they hit some kind of peak velocity in the middle, and then their velocity tends to drop off. The difference between where they hit the peak velocity and it starts to drop off is where acceleration hits zero. So did they accelerate at any point in time along this track? And if so, where was it? Was it at 10 meters? Was it somewhere at 40 meters? Or any time in between? So that's our goal. So in order to be able to do that, we just need to cover some theory. Remember, with the theory, I don't expect you guys to be masters of calculus or anything like that, but you have to be fairly familiar with slopes. And if you at least understand that, then the application side of things will be significantly easier. Alright, so you have already constructed a graph. It's just a normal graph where we have a y-axis and an x-axis. I'm going to keep it fairly simple for now. Again, it's the principle of calculating a slope that's important here, and then we'll look at how does that differ or change for a curved graph. Okay, so this is a straight line graph. Remember, the equation for a straight line graph is generalized as such. Y is equal to mx plus b. So somewhere in the recesses of your mind, this should all look somewhat familiar, where this m denotes the slope, or in other words, the steepness of the graph. So if this is a really small number, what you'll find is that the steepness of this graph will be relatively flat. If this is a really large number, it means that the steepness of this graph is fairly large. So it's got quite a large steepness. This b value denotes the intercept. So in other words, it's going to denote where does this graph cut the y-axis whenever x is equal to 0. And in other words, what this tends to do is that it'll shift the graph up or down depending on this particular value. If it's a negative value, this graph will be shifted down, and if it's a positive value, this graph will be shifted up. If it's 0, then it means that y is 0 whenever x is 0, and that's kind of what we're seeing here. How do we calculate what the slope is? Well, traditionally, and I'll show you guys the traditional way, and then I'll show you guys the way that we'll need to become a little bit more familiar with. The slope is calculated as the change in y over the change in x. Let me actually simplify that a little bit more. It's calculated as the rise divided by the run. In other words, that's stating the change in y over the change in x. In essence, what it tells us is the slope is an indicator of how much y will change for every 1 unit that x changes. Okay, so as x goes up, by what factor does y go up? What is the steepness of the slope? Is basically what it's trying to tell us. So if I try and simplify this a little bit more, the change in y is simply some final y position minus some initial y position, and the change in x is the same principle. It's some final x position minus some initial x position. Okay, so if I just try and make that relative to this particular graph, I can literally pick any point in this graph. So I'm just going to try and simplify it and pick 2 specific points. So I'm going to use this point and just 1 point ahead. Okay, remember, every point will have an xy coordinate. So if I pick this particular point, the x coordinate over here is 2 and the y coordinate over here is 4. So that's the coordinate of that point, and the coordinate of this specific point in terms of x and y is 3 for x and 6 for y. In terms of just generalizing it, it's my initial point and some future points. So this is the initial x position, and then this is the initial y position. This point over here in my particular analysis is the final x position, and then this is the final y position. So what I'm trying to find out is what is the slope between these 2 points over here. Okay, so if I just kind of draw a little triangle over here, this over here is my change in y, and this over here is my change in x. That should hopefully be somewhat familiar. All I have to do now over here is plug in the values for these specific coordinates. What is my change in y? What's my change in x? So my final y position is this number 6 over here, minus what my initial y position was, which is over here, it's the number 4. and divide that by what my final x position is, which is 3. Remember, the final is always some future point in time. So if we think about time progressing forward, 3 is ahead of 2. It's some points that happened later, and 2 is the initial portion, right? And I could have chosen any 2 points along this graph in order to get this slope. My initial x position is over here, which is 2. So then my slope is 6 minus 4 is 2, and 3 minus 2 is 1. So it's saying that y will change by 2 units for every 1 unit increase in x. Okay, so we would just summarize that as 2. So the slope, or this y, this m value over here, is a value of 2. B, as we said, was 0, so I could rewrite this formula as y is equal to 2x. That's going to be the equation for this specific line. And what you would realize is, if I had to repeat this for any 2 points on this specific graph, you would find out that the slope is 2 at any point. So the slope of this entire line is 2 the whole way through. Alright, so hopefully that's some fairly straightforward revision. What I want to try and do now is just kind of rewrite this in a format that might seem overly complicated, or might seem a little bit more complicated, but at the end of the day, what it's going to allow us to do is apply this same principle to any graph. Whether it is curved or straight, it doesn't matter. The principle will be the same. How do we find the slope of a graph at any specific point in time? Okay, so I will call this point over here A. So A is just a placeholder. I can put any number in. I'm just going to apply the same principle. Like I said, I'm trying to generalize it, and then at the end of the day, we should get the same exact principle, and then we can use our new principle to apply to any kind of a graph. Alright, so if I just call some point along this x-axis A, and some future point, I will just call A plus h, where h is just this change in 1 unit. So that's just going to be h. So you'd see this over here would also be h, and this over here would also be h. So h is just the change in 1 unit of x. Okay, and in terms of y, this will be the y position when our unit on the x-axis is equal to a, right? So if a is equal to 2, then this would be the y value when a is equal to 2. So that's something that we've already looked at. So if this is my graph for this equation, if I put a 2 for the value of x, my y value will be 2 times 2, which is 4. So at x is equal to 2, my y is equal to 4. Okay, so this is just a general format of writing it. So a is just a placeholder. What's the y value at a? That's given by this specific point. And then here at some future point, this is just going to be the y value at a plus h. Okay, so if it's this specific x value, which we've just kind of renamed a plus h, or just whatever the a value is plus this change in unit, will give me that specific value. I will get the y at that specific point in time. Okay, so now how do I calculate the slope? Well, slope is still rise over run. So it's still going to be this change in y. So I take my future y value, so it's just this y of a plus h. So remember, this is now calculating the slope, right? Y of a plus h minus the previous y value, or the initial y value, which is just y of a, over my future x value, which is just this a plus h, minus my initial x value, which is just this a. And what you see is I have a plus a and a minus a, so these will cancel, and I'm just left with the h. So it's some it simplifies to ya plus h minus y of a over h. Okay. And you might say, well, what the heck is the point in that? Like, that doesn't help me at all. That seems way more complicated than this. You will see the application of it in a second. Alright. So, if this is still our formula for this specific graph, I want to use this concept of finding out what the slope of this particular formula is. Remember, the x value is whatever the unit is that I'm using at some point in time, right? So y of a plus h is just telling me what the y value is at that specific point in time, right? So I could substitute what y is equal to by putting this value in here, where the x becomes whatever the equivalent is, right? Same here. So this a plus h is just whatever x is on the x-axis. So I could say 2 times a plus h, where the a plus h is just substituted this x, minus 2a over h. Okay. So this is the slope. That's what we're trying to find out. What is the slope of this particular graph? So this just simplifies to 2a plus 2h minus 2a, all of that over h. So then that simplifies. You can see I have a plus 2a minus 2a, so I have 2h over h, 2h over h. H's cancel, and I'm left with 2. Right? That's exactly what we said before. The slope of this graph is 2, slope of this graph is 2, and using this format of the equation, I get the same slope. Okay. Why is that useful? Well, what you've realized is that I can simply substitute whatever equation I have for a specific line into this formula, where whatever the value of x is simply substituted by this future value, and whatever the value of x is the initial value. So this is in essence is still the same as saying what is the yf minus yi. Same principle. We're just being a little bit more specific by using these kind of placeholder values. So it doesn't matter where I say a plus h is, or where the value of a is, the principle stays exactly the same. Okay, so hopefully that makes some sense. The question now would be, how does this apply to a curved graph? Alright, so let's show you guys that. So let's say, for example, here I have a graph that has a curve in it. Actually, what I want to do is to simplify this graph a little bit more. So let me just redraw it before we get to the specific one. So I'm just going to draw another set of axes over here. We'll still call it y, and we'll still call it x, and it's going to look something like this. It's just got one curve in it. Alright, and the equation for this specific graph will just be y is equal to x squared. Remember, our goal is to be able to find out what the slope is at any point in time on this curve. So again, I would basically pick two specific values, right? And I draw a straight line through them, and I want to say, well, the slope of this curve at these specific points in time is going to be equal to whatever the equation of this curve is there. You would notice though that the slope over here is in the opposite direction. This would be some kind of positive slope, but this would be some kind of negative slope. So our goal is to find out what is the slope at any point in time. So I'd have to find some way of generalizing this, and I can do it exact same way as I did in the previous example. So again, if I call this a, and again if I call this a plus h, where this is some h value, some change in the x-axis, right, which we'll just call h, and then this point over here is just my y value when the x value is equal to a, and then this is just y of a plus h. Okay, so we said that the slope would follow this formula where it goes y of a plus h minus y of a and all of that over h, right? And then we said, well, I could substitute the equation into this where the x, whatever happens to x, is just substituted by some other future value or some initial value. So we said the equation is equal to y is equal to x squared. So we want to generalize it and say, well, what's the slope at any specific value of x? So how much does the value of y change for any given input that I have of x? Well, like I said, whatever happens to x, I simply replace it by this y plus this a plus h. So instead of having x, I have a plus h squared. So this is now for the slope, minus a squared, right? So the x value just gets replaced by whatever I have in here, and all of that over h. So then that becomes a plus h squared is just a squared plus 2 times ah plus h squared minus a squared, all of that over h. And then I can simplify that a little bit more. You can see that there's a positive a squared minus a squared, so those cancel out, and then I have a 2 times a plus 2 times ah plus h squared, all of that over h. So I can factor out an h here because there's h in both sides, so I can kind of rewrite this as h, factor it out, times 2a plus h. So if I multiply these together, it'll be 2ah. That's exactly what I have here, and the h times h gives me the h squared divided by the h over here, and you can see that the h's cancel, and again I'm left with 2 times a plus h. Alright, so that would be the slope between 2 points. If I wanted to find out the slope at any one specific point, so let's say for example just at this very specific point over here, I just want to find out what is the slope at that point rather than between these 2 points. Because if I find the slope here, this is the average slope between these 2 points. So all I have to do is try and make this h smaller and smaller and smaller and smaller. So as I make this smaller, I'll eventually get to a point where I find the slope at just this one instant over here, the point that I'm interested in. Right? So that means that h over here just gets smaller and smaller and smaller. I'm bringing this dot closer and closer and closer, and I'd find the slope at a point rather than between 2 points. So in order to count for that, I just say, what is the limit of the slope as h tends to approach 0? Right? So as this value of h tends to become smaller and smaller and smaller and eventually approaches 0 or some really tiny infinitesimally small value, in essence this whole h tends to disappear and I'm just left with 2a. So this in essence becomes, or the slope becomes 2a. Okay, so it's just at that specific point. Alright, so that might still not make sense, but remember a is just the substitute for some value of x. Right? So in essence, the slope of this graph is equal to 2x, right? So if I want to find out what the value is for any x value on this graph, I can just say it's 2 times whatever the value of x is. And you should see there's some close link here between this 2 at the top somehow coming down and then nothing being at the top there, right? So maybe there's some kind of link, some kind of pattern that I start establishing here. So what I want to try and do now is I'm going to change this graph slightly and see if we can come up with what that pattern is. So let's say I change the value of this equation. So let's say y is equal to x squared plus, let's make it 3x. Alright, so that's going to be a slightly more complicated graph. And what I want to find out is, well, what's the slope going to be at any specific point? So I'll still follow that same thing. Slope, right, is equal to this ya plus h minus y of a. Remember, I'm still picking any 2 points, divided by h. Okay, so remember, the a plus h is just a placeholder for some future x value, and this a is just some initial x value. So whatever this formula requires me to do to the x, I'm just going to substitute it with that a plus h. So this becomes a plus h squared plus 3 times a plus h, so that's this whole formula, minus a squared plus 3 times a, and all of that over h. Okay, so this then becomes a squared, as we had before, plus 2ah plus a squared plus 3a, I'm just multiplying this out, plus 3h, then I just multiply this out by this negative, minus a squared, and a plus times a minus, this gives me a minus 3a, all of that over h. So let's see what I'm left with now. So plus a squared, I have a minus a squared, I have a plus 3a, I have a minus 3a. So again, I'm left with 2ah plus a squared plus 3h, and all of that over h. So let's see if I can factor out an h over here. So I've got h times 2a plus 3 plus a squared, and all of that over h. So I can't quite factor that out, so actually let me undo all of that. I'm going to leave it in this, I'll leave it in this format, where this will simplify as to 2a plus a squared over h plus 3. I just want to make sure that oh wait, silly mistake. I was wondering why this isn't working out. This a squared over here is meant to be an h squared. So this is meant to be an h squared. I'm sorry, hopefully I didn't confuse you guys too much. So I have a I have a 3a, I have a minus 3a, I have a squared, and I have a minus a squared. So I have 2ah plus h plus 3h, all of that over h. So now I can factor out the h. Plus a h, yeah, so that's h squared. 2ah plus h squared plus 3h. So I can factor out an h, 2a plus h plus 3. All of that over h, cancel the h's, and I'm left with, again, I want to find out what the limit is as h approaches 0 of 2a plus h plus 3. So you'll see as h approaches 0, this h will ultimately disappear, and I'm left with 2a plus 3. Alright, so remember a is a placeholder for x, so the slope, in other words the change in y over the change in x, for this particular graph is going to be 2x plus 3. So again, there seems to be some link between this 2 at the top here coming forward and disappearing at the top, and a 3 here multiplied by something which gives me a 3, and the x disappears. So these two seem to be linked somehow, and what it ends up being is that the slope, the change in y over the change in x, can always be defined as some value in front of the x, right? multiplied by the exponent. But the exponent will come down, so it'll be n times whatever the number is in front, and then it's the exponent minus 1, which will give me the slope. So let's just see if that will work here. So I take whatever the exponent is and multiply it by whatever number is in front here. So technically speaking, if there's nothing in front here, you could just put a 1 there. So this would be just 2 times 1. So let's just see if this works. So that's 2 times 1 multiplied by then the x times this exponent minus 1. So 2 minus 1. Okay. Plus, and we'll do the same thing over here. So an exponent, technically anything to the power of 1 is itself. So there's a, technically speaking, a 1 over here. So it would be the exponent. So this would be 3 times 1 times x times the exponent minus 1. So this would be 1 minus 1. So then this becomes 2x to the power of 1. Remember, anything to the power of 1 is itself. Plus, this becomes 3 times x to the naught. But anything to the power of naught is just equal to 1. So this becomes is equal to 2x plus 3. And anything to the power of naught is just 1. And I have 2x plus 3. Awesome, that seems to work really well. Let's see if that same principle applies over here. So if I want to find the slope, how much does y change with respect to x? It's equal to this exponent multiplied by the number in front, so that's just 2 times 1 times x to minus 1, and that just becomes 2x to the 1, and anything to the power of 1 is just itself 2x, and I think we've solved it. So now it doesn't matter how complicated the equation is for a specific graph, if it's got 2 curves in it, 1 curve in it, or 2 curves, or however many curves it is. The slope, the change in y with respect to x, is always going to be following this specific formula. So eventually when we get this type of a graph, which is a polynomial to the third power, we can find out what the slope is at any specific point in time. Why would that be of any interest? Well, if I have a position versus time graph, the slope of that graph is going to be equal to velocity. So let's say that this was the position and this was time. So remember, the slope at any specific point in time is the change in position. We'll call this maybe change in x, and this is change in t, right? So the slope is equal to the change in x over the change in t. And remember, velocity is defined as the change in x over the change in t. So this is equal to velocity. And I'm sorry if I rushed this last part, but I'm just running a little bit out of time. But this is one of the reasons why we want to be able to find the slopes of specific graphs. The same thing applies when I have a velocity versus time graph. Then the slope of that graph gives me the acceleration. Right? So the same principle applies. If I can find the slope of a graph, or if I have the equation of the graph, I'll be able to find the slope at any specific point in time. That's how I get instantaneous velocity and instantaneous acceleration, which is going to be super useful for our Prac. So I'll show you guys how this applies in the next video.